Let me welcome you to this lecture. We have now discussed the chemistry of metal borides as well as the chemistry of hydrides of boron, that is boranes. We will now discuss the chemistry of another important class of compounds formed by boron, that is we will discuss the chemistry of boron-oxygen compounds. In fact, all naturally occurring compounds of boron contains boron-oxygen bonds, and boron is not naturally but does not occur naturally as elemental boron. Neither any naturally occurring boron compound has uh, boron to any other element bond apart from boron-oxygen bond. So the boron has strong affinity for oxygen, and in fact uh, the structural complexity as well as diversity of some of these boron-oxygen compounds are comparable to the structural diversity or complexity that we see in case of metal borides or the borates. And we will discuss about different types of boron-oxygen compounds here. So let us first begin with the oxides of boron, and that is one primary oxide of boron is B2O3. It is known as boron sesquioxide. The word sesqui here means 1.5 because for each boron atom here we have 1.5 oxygen, so we call this boron oxide as boron sesquioxide. Now this particular compound, that is boron sesquioxide, is a very important compound industrially because this is used for manufacturing of borosilicate glasses. That we use in the laboratory. All glasswares are made of borosilicate glass. The one specific property of borosilicate glass is that its the coefficient of thermal expansion for such borosilicate glass is very small, and that is why we can use these glasswares at different temperatures, at quite high temperatures as well as in low temperatures, and the glassware still remain intact because of this property of borosilicate glasses. Now this boron sesquioxide, or all oxides of boron, these are non-metallic oxides, and that is why they are acidic in nature, and these acidic boron sesquioxides essentially react with basic oxides like metallic oxides to form metal borates. So because these are acidic in nature, they will react with metal oxides MXOYC to give us metal borates, and we will learn about metal borates. These are again another important class of boron-oxygen compounds, and this particular aspect of formation of metal borates is essentially used in qualitative analysis of metal ions or basic radicals. We have already probably done. During qualitative analysis, we do a test known as Borax bead test. So in this Borax bead test, what we do is that we take a platinum wire, we make a loop on a platinum wire, and then we put some amount of either B2O3 or borax. So the formula of borax is Na2B4O5OH4, and it also contains 8 lattice water molecules. So either you take B2O3 or borax powders on top of the loop, on platinum wire loop over here, and then you place some amount of the metal salt, and then you heat it on a Bunsen burner. So what you do is that the metallic salt is essentially converted to metal oxide when upon heating, and then it reacts with either B2O3 or borax to form metal borates. Now these, so what we get essentially is a glass-like metal borate bead. So that is why we call it borax bead test. And these beads or these metal borates have specific color depending upon the metal that is present in your mixture, in your salt, and based on the color one can identify the metal that is present. So by doing this, in fact, what was found out that in vitamin 12 the presence of cobalt was identified by using a borax bead test initially. So the cobalt oxide will react with say B2O3 during borax bead test to give us cobalt BO2, and this particular metal borate has characteristic pink color, from where it was identified that cobalt is present in vitamin B12. So the borax bead test is very important test in qualitative analysis of basic radicals. And then let us discuss about the oxo acid of boron, that is about boric acid. So H3BO3 is it's a monobasic acid. Note there are 3 hydrogen atoms. It is a monobasic acid, and this boric acid does not donate H plus ions, but instead it only accepts OH negative ion, and that is why one can denote it as or term it as a Lewis acid, not as a Bronsted acid, because H2BO3, or just write it as BOH3, it will accept OH negative ion and essentially result in BOH4 negative and H positive ion, and that is how it acts as a monobasic acid only. Now this is a weak monobasic acid, as the rate of dissociation is very poor, but what one can do is that when we add a cis diol, then the rate of dissociation can be increased, or this equilibrium can be shifted towards this side, so that H positive ions are formed. So during the titration of boric acid with sodium hydroxide, that is why one adds cis diols. So cis diols are added during the titration of sodium hydroxide, a strong base with this weak acid, boric acid. Because when we add cis diols, what happens is that cis diols are going to react with boric acid over here to result this sort of chelated cis diol complex here. And when another mole of this cis diol reacts, we end up with so during the titration of boric acid with sodium hydroxide, when we add cis diol, the this is BOH4 negative. So BOH4 negative ions that are formed in the after dissociation of water here with boric acid, these BOH4 ions will be trapped by the cis diol here to form a stable chelated complex. So the equilibrium cannot now shift towards the equilibrium will be favored towards the right hand side over here, and this will lead to dissociation of water to H positive, and that is how the titration with sodium hydroxide can now will be accelerated because we shift the equilibrium towards the right hand side by addition of cis-diol, or we increase the dissociation of boric acid due to the addition of cis-diol, which forms a stable chelated cis-diol complex with BOH 4 negative ion that is formed after dissociation here. So that is how that is why it is important to add cis-diol during the titration of boric acid with sodium hydroxide. So let us now discuss about metal borates. We have seen that earlier that reaction of B2O3 with metal oxides leads to formation of borate metal salt-like compounds, which are known as metal borates. We have different kinds of borates formation depending upon the metal and the condition. And these borate structures, or when one looks at the borate structures, what one finds is that there can be boron atoms, which boron atoms can have 3 oxygen atoms attached to them, as well as boron atoms can have 4 oxygens attached to them in these metal borates. When 3 oxygen atoms are attached to the boron centers, the boron is the structure, the geometry on the boron is trigonal and planar. When 4 oxygen atoms are attached to the boron, then it becomes tetrahedral with sp3 hybridization. Here it is sp2 hybridization. Now, polymerization of these borate ions can take place here, and then this by sharing of these oxygen atoms, this this BO3 3 negative unit, that is BO3 3 negative unit here. Here it is BO4, that is 3 positive and 8 negative, 5 negative. These ions can form oligomers, and this is how we have a diverse range of borate ion formation or borate structure formation. So we'll see some of the borates that are or borate units that are present, that have been discovered so far. So when only one BO3 3 negative unit is present, then we call such borates as orthoborates. When only one BO3 3 negative unit is present in a metal borate, we call such metal borates as metal orthoborates. Now we can have, by sharing one of the oxygen atoms, this BO3 3 negative unit can form an oligomer, or that is, we can have this sort of borate structures. So these are all going to be negative charges are going to be present here. So this is B2O5 4 negative ion, and we call it as pyroborate ion. So further polymerization we call then metaborate ion. So we can have metaborate structures. This sort of metaborate structures can be possible. So one can have infinite chain formation in this way, and we call such structures containing infinite chains in this sort of chains as metaborates. So we can also have discrete metaborates, not only polymeric metaborates. So this sort of borates or cyclic metaborate, this is cyclic metaborate with the formula B3O23456 3 negative. So again we see these cyclic metaborate units are formed by sharing of two of the oxygen atoms on each of the boron center here, and that is how we obtain cyclic metaborates. While the linear chain metaborates, again two of the oxygen atoms are shared, but here we have a chain structure formation, while in this case the chain essentially joins up, and then that is how we obtain a cyclic metaborate structure here. So we also have borates with 4 oxygen atoms attached to the boron center, and one such example where 4 oxygen atoms are also attached to the boron center is the borax ion. That is, we know, we have seen the formula of borax ion B4O5OH for 2 negative is the formula, and the structure of the borax ion is very interesting. So we have 4 boron centers, 5 oxygens, and 4 OH groups in this way, and these boron centers, which are tetravalent, they will carry 2 negative charges, and that is why this ion is 2 negative. Overall, this ion has 2 negative charges on it. Another interesting borate with tetrahedral boron center is, we can write so this is another type of boron where we have now a spirocyclic ring structure is present in this borate ion, and there is when one of the boron center is attached to 4 oxygen atom, and again it carries a negative charge, and because of this its structure we call it spiroborate ion. So this is a very interesting example of a borate anion. We can also have peroxo linkages in a borate ion, and then when peroxo linkages are present in a borate ion, we call these borates as, or borate ions as, peroxo borates. And these peroxo borates are important industrially because they are used in detergent powder as whiteners, and the structure of one of these peroxo borate we can see. So these are peroxo linkages what we have over here, and then we have this is a peroxo borate ion that is formed or that is used in detergents. So this essentially brings us to the end of this lecture. What we have seen during this lecture is, or we have discussed about different types of boron-oxygen compounds. We have seen, we discussed about boron sesquioxide initially, and why it is important in qualitative analysis, because one can use, or one uses this boron or the metal borates formed by this boron when we treat metal oxides with boron oxide, or when we heat a mixture of boron oxide, sesquioxide with metal oxide, and we obtain metal borates, and these metal borates have specific color depending on the metal, and that is how one can identify different metals by using the Borax bead test. And in fact it was this Borax bead test initially allowed to find out that cobalt is present in vitamin B12 or in cobalamin. Now, after that, we discussed about the oxo acid of boron, that is boric acid, and we learned that it is a weak monobasic acid, and one can term it as a Lewis acid, not as a Bronsted acid, because it does not donate H plus ion, but it only accepts OH negative ion. And we have seen how one can increase the rate of dissociation or increase the acidity of the boric acid by addition of cis diols, because cis diols form stable chelated complexes with BOH4 negative ion, and that is why cis diols must be added during the titration of boric acid with sodium hydroxide in order to obtain a sharp endpoint, or otherwise the reaction is going to be inordinately slow, so that one cannot do the titration in fact. Then we also learned about metal borates, and we learned about different types of metal borates, and we draw the structures of different borates. So we started with orthoborate ion, then we saw the pyroborate ion, and then we went on to draw the structure of metaborates, cyclic metaborates, as well as polymeric chain metaborates, and finally we have drawn the structure of borate ions, where boron atoms are attached to but 4 oxygen atoms, or tetrahedral boron atoms are present, and we have drawn the structure of borax ion as well as pyroborate ion, and then finally we have seen peroxoborate ions, where peroxo units are also attached to the boron centers. Apart from these compounds, another class of compounds that are important, another class of boron-oxygen compounds that are important are organic compounds containing boron-oxygen bonds. So we can have boron compounds of this formula. This is known as boronic acid. So in fact, one of the Nobel Prize in chemistry was awarded to a reaction where boronic acid reacts with aryl bromides using palladium catalyst. So this gives us a CC couple product essentially. So when the R must be again an aryl group in this reaction, and this reaction is known as Suzuki-Miura coupling reaction, and because of this discovery, again, this reaction was awarded a Nobel Prize in chemistry, and that is why one more use of this boronic acid is when one takes these boronic acids and then heat them up, dehydration reaction is going to occur, and one ends up with interesting structures. These sort of structures can be obtained. These are known as Boroxens structures. Now, if one takes a diboronic acid or polyboronic acid, say if we take a polyboronic acid in this fashion, and then we heat this up, what is going to happen is that because we have BOH units in this way, so these BOH groups are also going to undergo condensation when we heat this, and then this will lead to formation of a crystalline polymeric structure, and such materials are of lot of interest nowadays because of their application in many industries. So let me conclude this lecture with this, and I thank you very much for being with me during this lecture.